Baylor. At that time only, he just entered, and I think he's going to finish his PhD soon, and have prepared a manuscript which is going to submit to a very high quality journal. I am not sure, but he may put insight into that. Also, so this session is being organized particularly for having a hands-on experience on ambient noise tomography using the Python routines that are available on GitHub with the name of G2, I think. I'm not sure. Okay, so Mr. Debjeet Barman, he did his master's from IIT Kharagpur in 2016, I suppose.
13.
2013.
Yeah.
Oh, so he did his master's in 2013, and then subsequently he joined Baylor. And he's a very fast friend to me and to Ritam Vishwas, and he's also doing some work in collaboration with Professor Mridul Sen at UT Austin. Not only that, we have been roaming around during our time at Baylor within the city of Waco and also in Austin at various places, and had a lot of fun together. So, like right now, I am seeing my lab and getting nostalgic about that particular location where we were sitting together and enjoying our days there.
Yeah.
Although it was very much quiet, it is a very quiet place.
Yeah. It's
like,
quiet, yeah.
because not only due to the COVID, but generally also it is very quiet. I came to know that this time. I think last year Waco got some snow also. So that's a very good place, and you can see like the facilities they have in the lab. They have a big sofa at the back where they can sleep anytime during the night and whenever they are getting tired. So that's quite a very nice lab. I think it is in terms of facilities, it's the best lab in the Department of Geosciences at Baylor.
Yeah, I think so. I think same as well, yeah.
And Debjeet is still working on the same computer, which I think he was working since from the last 4 and 5 years on the same computer that is in the center of the lab.
Yeah, it's a center of the lab, yeah.
So is there any new additions in the lab? Like I can see there is a big monitor at the back.
There are two new computers over there on the back side. And they replaced one of these computers. I think they replaced the Polar. Also, there's an add-on computer over there at Diego's place.
So is this lab is being shared with some other faculty as
well? Yeah, Peter James.
Okay. So now I would like to welcome, I would like to request Debjeet to start with the session. So let me tell you, Debjeet, Dheeraj is the person, Dheeraj Kumar Singh, who just came online with his video.
Yeah.
Dheeraj, is it possible to come on video? If possible, you can replace with Ravindra also, because it's okay.
It's a noise.
It's fine. Video is not. It's fine. Like okay. So yeah. So first of all, my name is Debjeet Barman. I think Mohit sir introduced me to you, and so basically this whole thing we can distribute in 3 parts. First of all, basic intro of the ambient noise tomography, like what it is all about, the physics behind it. And the second thing is that like the process, like and process also the importance and also its drawbacks, like where we cannot use this thing, and also the pros. And the third part, we'll discuss the code, the basic skeleton of the Gutenberg code to process the ambient noise, as well as to invert the Green's function. Later I'll discuss this Green's function stuff to get a more relevant tectonic or geologic and maybe crustal model, as we can say. So let me start with this introduction to the ambient noise tomography. For this thing, I want to introduce to this paper. It's available. It's published on 2010. It's by Wapinar. He is one of the founder of ambient noise tomography other than Clairabout. So let me share my screen. That will be good. Can you give me the permission to share my screen? I think it is asking.
Yes, now you can show.
Okay. Can you see my screen?
Yes.
Okay, let me. So can you see the okay, so this paper is published on 2010. It's a very basic tutorial paper, and there are two tutorial in this ambient noise. Sorry for that. The part one discusses the very basic principles and applications. So let's before going I don't want to read this paper right now. So I'm going to the fun part, like what is it all about, and I can tell you in any very foundation level language. So let's say, I think you can see this figure 1, right? So in this figure 1, you can see there are 3 points. Can you see my mouse pointer as well?
Yes, sir.
Can you see my mouse pointer?
Yes.
Sir.
Okay. So there are 3 locations over here. It is signified. It's XS, XA, and XB. So this is the space, and there are 3 receivers placed at there are 2 receivers placed at XA and XB. And let me know if my voice is not audible to you. So let's say there is a source which is originating from the point XS, and we assume that source is a line source, which means the wavefront coming from this source is a plane wavefront, which means the plane wavefront means just like it is kind of vertical wavefront, and it is just propagating from left to right. So let's say if we observe the waveform at XA and XB location, receiver locations, for different time samples, we can see the figure, this figure, figure B. So let me explain what it's happening over here. So this figure B tells you at what time the wave reaches at XA. So let's say if the wave starts from XA, which means at the starting location, the travel the t equal to 0, as simple as that. And let's say we observe the wave at XA at time TA. Okay, so similarly, if we do the same thing for the receiver B at XB, you will observe the same waveform which is originating from the XS location at time TP. So which means that we are observing the same waveform at time TA at XA location, and we are observing the same wave at time TB, seconds or minutes, something like that, for XB location. So now, let's say now, assume you don't know the exact location of XS. Let's say we don't know where the actual epicenter or the origin of the source is. So in that case, we can assume one of these two receiver locations as source, and which means that for this figure, I'll go back, like maybe I'll show you later the other figure too. Let's say assume for this figure, among these two receivers like XA and XB, if we place the same source as XS at XA location, the same wave will reach at XB at time equal to TB minus TA. Let me repeat this sentence once again, like I can reframe the sentence what I just told you guys. Let's say we have the wave arrived at time TA at location XA, right? And we have the same wave observed at time TB at XB location. So now let's say, now forget about the origin of the source and all. So if you consider if B and C, not the A, you can see the same wave. The wave is common for A and B, means XA and XB location, which means if we assume that XA as source, it's an assumption. Let's say if we assume XA as the source location of the wave, then at XB, the arrival time with respect to XA will be TB minus TA. Let me know if if you have any confusion regarding this explanation. It's a very simple explanation. So, which means we have observed the wave at XB at time TB minus TA with respect to position XA, not with respect to position XS. As simple as that. So this is the basic fundamental figure of this ambient noise tomography, which means, let's say if you don't have the earthquake or maybe any kind of seismic sources, let's say if you remove the excess, you can still recreate or reconstruct the seismic waves by using a pair of receiver locations like XA, XB pair, something like that. So this kind of simple ambient noise reconstruction is often called like 1D Green's function extraction or direct wave reconstruction, which means the wave is directly propagating from XA to XB, and it's not a surface wave. For this, it's not a surface wave. It's just a direct body wave, like P wave.
Excuse me, sir.
So similarly, let's. So there is a proof behind that. Like if we, I'll go to the proof later after telling you the basic.
Excuse me, sir.
Sorry.
Sir, I have a question. So when we are considering the source, whatever the wave it is emitting, we are considering it is a plane wave. Okay. So there might be some criteria between the source and the receiver distance to consider as a plane wave, because when we are considered as a plane wave, so source should be very far away. So is there some criteria that to select assume it as a plane wave?
Yeah, so I'll come to the that part like in the later section. Like yeah, so that's the important thing. Yeah, so that's what I'm talking about right now. So what's the assumption? And there are several assumptions regarding that. So first of all,
I think what Hiran is saying, it's true for a point source. Okay, if it is a very largest distance, then it may be a wavefront that will be looking like as a planar wavefront. But if it is a line source, then it will already be a plane wavefront, right?
Yeah.
So in a line source, so what we are telling, that means you are talking about the array that is perpendicular to the receiver direction.
Yeah. So it's a just an example. It's a kind of cartoon diagram. So I'm I'll come to that actual thing right now. So just like keep up with me, and you can, I think you can understand the whole physics of it. So so in the next part, let's come to the one example of this 1D thing in the real time, not with the synthetic results. So there, in this figure, in figure 2A, you can see there is the 2A corresponds to the response or the waveform observed at location XA, and B, this figure B is corresponds to the waveform observed at XB location. So if we find the time lag between these two waveforms, we can get the actual signal over there. So to calculate the time lag, we often take care of this problem by a cross correlation function. It's very efficient, it's very fundamental function. And the cross correlation actually, which cross correlation of this these two waveforms will provide you the Green's function of, or the time, or the arrival time, basically in terms of time lag. So another thing, let me tell you like why we are telling that it's a Green's function, it's not a actual waveform. Like in the figure C, like from the figure C, you can see after cross correlation, you will getting the time lag, which means the arrival time of the same wave at XB location with respect to XA location. But still it's not an actual wave, because first of all, it's an impulsive response of the system. Like it's not the actual wave, because as we know, I think you already studied in your undergrads that the basic fundamental convolutional criteria of the Earth. Like as we know, the Earth is a low pass filter, so we can assume that Earth as a convolution, like Earth, the response of the Earth, we can convolve with the external source to obtain the observed response, right? So in that case, as we don't know the exact source or exact waveforms or exact waveform signatures at source location, which means we cannot deconvolve to obtain the Earth's response. So over here, what we are getting when we are obtaining the cross correlation between these two waveforms, it is giving the impulse response, like impulse response, which often means the deconvolved like the response which we get after the deconvolution from of the observed seismogram to remove the source signature. So this is often called the Green's function. So let me go back little bit to give a brief overview using some of the equations. I think if I cover 2-3 equations, you can understand the whole physics behind it. So over here, let me know if you can see the highlighted part of the equation I am just highlighting in the paper. So let's say this is the Green's function. Can you see the highlighted point? Hello?
Yes, sir. Yes, sir. Yes, sir.
So,
it's visible.
yeah. So let's say GXAXST is corresponds to the response at XA. Similarly, if we think that XB as like GXB XST is a response at XB location, so then the cross correlation will provide you the time, the lag, which is often called this. Let me go back to this one. Like you will get the TB minus TA after the cross correlation. So the cross correlation of this two waveforms in terms of physics, we often write as this. It's not as just the Dirac delta function. It's Green's function, because I already told you the same thing, that it's an impulsive response. So now let's see. I think I just told you guys that the impulse response will convolve with the source wavelet, give you the observed seismogram, right? It is valid for XA as well as XB. So if we consider the source wavelet is a stationary phase wavelet, and the autocorrelation is SST, and autocorrelation is just as ST convolved with S minus T. I think you know about that. So the cross correlation function can be written in this form, right? Like where u xb xs and u xs are the actual seismic responses. Okay, so now what happens that if the source is not an impulsive source, let's say some kind of uh, some any different kind of maybe binomial function or recorrelate, maybe some other kind of function is there. In that case, we should use this function instead of the direct cross correlation. But as we assume that uh, the phase of the source is stationary, or maybe if it is non-stationary, like if the amplitude spectra is like it's scaling it up, like that convolution in frequency domain is nothing but the multiplication, right? So which means that, let's say if you consider this equation number 2 in frequency domain, which means if you divide this multiplication with this one, the autocorrelation function in frequency domain, which is nothing but the Green's function, right? As we know that in most cases for our study and like ambient noise study, it's the effect of autocorrelation function of the source, it's quite lenient. It's not like very spiky or irregular. It's kind of nominal, the autocorrelation function in frequency domain, which means if we scale down the actual seismic waveforms at different source or different receiver locations, we can get the actual impulse responses, which means it's independent of any kind of source signatures. So it's also an assumption. You should like think like in this fashion, like it's not true as like for all these cases, but we think like that. So similarly, like if we consider the source is coming from this side, from this figure 3, like from the right to left, like it's arrives at xb first and xa later, the arrival time will be the with respect to xb will be at tb dash minus tba, right? Similar derivation for this one as well. So now let's come to the fun part where we have I think this is also taken to be granted. I think if you consider two sources coming from both sides, you will have one over here, like in figure 5, you can see, like if you have like figure 4 and figure 5 are related. So figure 4 has the skeleton of the source locations and receiver locations, and the figure 5 corresponds to actual responses. You can see if we consider the source, there are multiple sources, one coming from the left hand side and one coming from the right hand side. So if we cross correlate those two responses from XA and XB for different scale, like for as causal part, like for positive time and for negative time, we'll get different spikes at different lags, right? So we'll get different cross correlation peaks. So now come to the 2D part. It's very interesting. You were talking about those linear arrays. So that's why the 1D part is different from the 2D part. The 2D part is much more realistic 2D and 3D analysis. I'll discuss 3D as well. 3D is like same as 2D. It's not different. But 1D is a lot different because in 1D we assume that wave is a plane wave and it's coming from that side because it's a direct wave, right? So what now 2D wave, let's say we have placed two receivers at XA and XB according to this figure, and we are assuming we have uniform distribution of sources around it. Like you can see those dots, like it's kind of like honeybee dots. these are the source locations of for regarding ambient noise. And we are assuming what we are assuming first. There are two assumptions basically. First assumption is that the source distribution is uniform, and second assumption is that we have only coherent phase sources. Coherent sources means the phase difference between these like the phase difference, I think you know that phase difference between the sources is consistent and it's same, it's not changing with time, which means we assume that sources are coherent. And coherent source means that the waveform will not distort with time. The waveform will be smooth, like the regular one, like it's not be distorted with increasing time. Like if the, I think you can see the mouse pointer over here, like if the wavefront from this source is coming like this and this, like this way, like it's kind of arc or spherical waves, anything you can consider spherical wavefronts, like according to a Huygens principle. But if the source is not coherent, in that case, what will happen? The source will be, sorry, the wavefront will be distorted with increasing time, and it can mess up with the result. So there are two assumptions. So let's now this figure B and see what it is telling about. The B is the observed waveforms at XA for different azimuthal sources. Let's say you the zero is over here, and if you go, like if you rotate it counterclockwise, the phi s is increasing. So with increasing phi, you can see the response is also oscillating. Like with, you can see over here, let's say start with 0 over here. If we can think as this as a reference point, with increasing phi, the distance is increasing, right? So it is like this, it is the time, the as the distance increases, the time is also increases, right? So which means that travel time from here to here, the XA location. So you can see the time is also increasing, like it is going towards down, down, down. And now after 180 degrees over here, again the same thing is happening on the other side. Means from XA to here, the distance is decreasing if you increase the phi, right? So you can see over here, and towards like if you go from -90 to 0, like similarly the phi is increasing, and also the time is decreasing from XA to these sources. So you will get this kind of observations at XA. Similarly for XB, like it's usually vice versa, because XB is over here, and the initially at 0th location, the distance is much more greater. And if you increase phi, the distance will go down, right? Like this, from 0 to distance will go down, so the time will go down. So that's why it is going up, 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 up. And after 180 degrees, you can see 180 degrees is the shortest distance at 180 degrees, which means after 180 degrees, the distance will increase, which means the travel time is also increased. That's why it is increasing. So now, similarly for the 1D and 2D, like similarly like 1D, if you just cross correlate these two XA and XB, just these two, like cross correlate these two for different phi sources, you will get this kind of thing, right? Let me, you can interrupt me anytime, at any time, if you have any problem. So you can see after cross correlation for different phi sources, for different azimuthal variation of sources, you will get the cross correlation function as this. If you have any confusion, let me know. Otherwise, I'm just continuing my explanation.
Sir, in figure B.
Sorry?
Yes, sir. I have a question. So it's, I think it's a little weird, but In figure B, as we see, as the phi is increasing, the distance is increasing. But in the time axis, what we are saying, at 0 degree, it should have minimum time because it's almost normal type.
For which one? For figure B?
For figure B, left side.
For figure B corresponds to the distance from XA, not XB.
Yes,
So
sir.
from XA, if you consider if you consider, let's say, if you consider zero azimuth is towards over here, right? From
Okay,
this
yes.
distance is much more smaller than the other distances, right? So if the distance is smaller, then the arrival time will be much more smaller, right? That's why it is going
Yes.
towards up, like it's towards lesser end, right?
Okay.
That's why, see, it's a much more lesser, because this distance is the least distance among
Yes.
all the distances available,
Yes, sir.
right?
Yes, sir.
So yeah, so if you cross correlate these two responses from these two stations, XA and XB, so after cross correlation for different azimuthal variation of sources, you will get this kind of spikes at different arrival times, like which can give us a overview of sinusoidal wave, right? So it's in this kind of sinusoidal wave, you can see the majority of the source or the majority of the response is coming from this region. See, can you see my mouse pointers?
Yes, sir.
This part and this part, the density is much more higher than the other parts, right? So it's a kind of observation. I'll let you know why it is happening, but first of all I need to continue for the second part, like for the next figure, so that you can get an overview why it is happening. Then I can explain back why it is much more denser over here.
So figure D is the cross correlation.
Yeah, for the figure D is the cross correlation of these two, like XA and XB for different phis.
Okay.
You can see, like,
Yes,
for
yes,
let's
yes.
say for yeah. So
I
in that,
understand.
yeah, so what is happening over here, like now let's say you have all the responses for different phi values, right? It is coming from here, here, but ultimately what you are getting, it's a collection of signals, right? It's a stacked up signal, which means, as we know, the from the property of basic characteristic of signal, that what we observe is the response from multiple sources. We assume like that for any kind of system. So in that case, what we think, we should stack this thing, right? Like we should add up all the response for all the phi value sources, which means we need to stack it up from the left end or the right end, not from the top or not from the bottom. So if we stack this up, you can see these middle parts, like this thing and this thing, are got cancelled, because this is positive and this is negative, right? And this thing, this part and this part is got cancelled. Are you getting my point?
Yes, sir.
Let me know if you have any confusion regarding that. So what is happening, that when you cross correlate this thing, like, as if you stack this value with this value and this value with this value, these are of opposite phases, right? Because the cross correlation you are getting from this end, what do you mean by that? This end cross correlation is defined by the response at XB with respect to XA for this region sources, for the fourth quadrant.
Yes, sir.
And the response at XB with respect to source at XA for the region for third quadrant is over here, and for the fourth quadrant is over here. Let me know if you have any problem. So what happens that because of the phase reversal, which means these things got cancelled, right? This things and this thing and this thing. What remains? These two part has the same phase. This doesn't have any like opposite phase thing because it is over here, right? If you stack this up, hello, hello, hello.
Yes, sir.
So yeah, so the thing is that you can see over here, this thing is got cancelled of this because of this part. This part is because of it's got cancelled because of this thing, because the phase is opposite to each other. But for this one, you don't have any thing like this one over here, right? So if you stack this up, this thing and this part got intact, and these are the remnant parts. So after stacking up, this the signal will look like this, the figure E. So now, why it
I
is
think,
happening like that?
excuse me, sir. So you mean to say, hello?
Hello?
Yes, sir.
Yeah. What's your question?
What I'm telling, so when you are telling the 0 to 90 degree, 0 to 90 degree and 0 to minus 90 degree, that 0 to minus 90 degree, that falls in fourth quadrant. Okay. And 0 to
Yeah.
90 degree, it's in first quadrant. So they, I think they might not cancel, because I think third quadrant will cancel the, sorry, I mean to say 90 to 80 degrees. Second quadrant will cancel to the fourth quadrant. Is it like that?
Let me explain. Yeah, like actually, let me explain in a different way, then you can get it. So the thing is that, like, I think something is missing. Like, I think you are missing something. So first of all, let me tell you that the thing you are seeing over here, the positive time, the lower section is the response at XB for XA, and the upper half corresponds to the response at XA because of XB.
Okay.
So what happens that when you cross-correlate the response which are coming from this side, let's say for minus 90 to 0 degrees, in that case, what will be the phase over here? Like in this case, like for for the observed response at XB because of XA for this section, what do you think about that? Like, is it be positive or negative? The cross correlation function, will it be positive or negative? Like the main phases or something like that. Like, let me reframe the question once again. I think you got this figure right over here in the figure 5.
Yes, sir.
In the figure 5, what you are getting that this part, the positive part is because you have the impulse response or the Green's function at XB because of XA, and this is the negative part, negative time, or the causal time is defines the response at XA because of XB. So if you just figure it out over here, you can see so this time, hello,
Yes, sir.
is my voice is audible? I think it's audible,
Yes,
right?
sir, it's audible.
So yeah, so what happens that, let's say let's consider this one. I think that will be much more easier for all of you guys. So let's consider this this response at XA. Can you see this one over here?
Yes, sir. Yes, sir.
And can you see the other or the same response at XB for the same azimuth, like maybe for 80 degrees? It's over here, right?
Yes, sir.
Hello?
Yes, sir. We are getting.
Yeah. So what happens that, like, basically, I think there is a confusion to all of you guys because of one certain things. You were thinking that like it is got cancelled because of some because of some kind of uh, nullify effect of the coming from different sources. Is it correct? Do you think like that? Then I can explain you in a different way, like what's happening over there.
Yes, I am thinking that.
Yeah, so the thing is that now don't go into this figure. Let me go into the actual physics behind this over here, like in figure A. Now let's see the source. Let's say consider this source, like the source at this from 180 degree to 270 degrees. Can you see this? And now consider this source. Hello?
Yes, sir.
Yeah. If you consider this source and compute the positive time response. Positive time response means XB means XA cross XB. If you cross correlate XA with XB for this part of sources, what we will get? Like the time, like I'm talking about in terms of time, like the time will be like the travel time from this minus travel time from this, right? Let me, I think I can draw something. Let me check. I think if I can draw, I think I can. Sorry, I can't draw. I think basic fact is that, let's say if you consider this this as a source, this part as a source, which means the travel time or the ray path from the source to XB will be like this.
Yes, sir.
And similarly for XA, like will be like this.
Yes.
So the time difference between XA and XB will be like this much.
Yeah.
Yes.
Yes, yeah, perpendicular. Yeah.
Yeah, perpendicular distance, right? Similarly for this one will be like this.
Yes.
But what will happen that if all these sources simultaneously act, it will cancel each other because you are also considering these sources as well as this one, as well as this one, as well as this one, which means, let me go back a little bit, then you can understand. So over here in this figure 4, you can see there are two simultaneous sources, right? Which is one is coming from left hand and the right hand side.
Yes.
So in this case, you can see two spikes are occurring, one in the negative end and one in the positive end, right?
Yes.
Yes.
So like why you are getting two by, like for two sources over here, because you are considering only this travel time along the x-axis, right? So there is no other sources in any other from any other direction which can nullify to each other. So let's say if I consider, like it often happens, let me tell you one thing. Let's say there is a source is over here. Can you see my pointer, mouse pointer near
Yes,
the
sir.
minus 90 degrees is
Yes,
just
sir.
the above. So in that case, the perpendicular distance between XA and XB with respect to this source will be 0, right?
Yeah.
Am
Yes,
I
sir.
correct or not?
Yes, sir.
So now let's say if you are going this way, it will the time difference is this much.
It will
Yes.
Okay.
increase.
And also for the other way around, like if you consider with respect to xb with respect, means if you do the xb cross xa instead of xa cross xb, in that case what will be a time difference? So time difference will be, or the perpendicular distance will be like this much, right?
Yes.
This much
Yes.
over
Yes.
here, and this is over here.
Yes.
Yes, sir.
So the collective effort, which means that the collective effort, what we'll get, this will have a projection, and this will have projection along this line, like along
Yeah.
X and Y
x-axis.
axis.
Horizontal.
X-axis.
Yes.
So which means that what you are thinking, that this phases got nullified, it's not like that. What it is happening, that like over here you can see the distribution of this impulse responses is too sparse. It's not getting zeroed. My point is that the nullification is not because of positive and negative thing. Like you don't think like that the amplitude is positive and amplitude is negative over here. It's not like that. Amplitude is positive throughout this series.
Yes, sir.
Throughout this, all these five, the thing is happening over here as the response for these 5 value sources is too sparse. You can see it's too, like if I can zoom, okay, if I zoom it, you can see the value, these squares or these wiggles are too sparse to each other. But over here you can see it's a lot denser, right?
Yeah.
Yes, sir.
So the thing, if you have any questions, let me finish this and you can ask me. I think I can answer your questions right now. So the thing is that when you stack this up in figure E, oh sorry, if you stack this up in figure E, you will have this responses, small ones over here. Can you see this small ones?
Yes, sir. Yes, sir.
But the majority of impulse response is over here. So again, I am going back. It's a very important part of this, of the physics of this thing. Why it is happening like that? The amplitude is higher over in this region. The amplitude is very lower in between. The main reason is that when you are considering the perpendicular distances, like if you cross this parabolic or hyperbola, it's not parabola, it's hyperbola. If you cross this hyperbola, like if you are in this region, what will happen? The perpendicular distance is much more lesser than xa minus xb, right?
Yes, sir.
If you consider this source or this source or this one or this one, maybe this one, or maybe this one, like it will always less than xa minus xb.
Yeah.
And it is very discrete, because as I think you know about the class 12 physics, right? We have done that s equal to r theta, right? We can measure the length of the arc from the radius of the curvature, also the theta in radian, right? The angle.
Yes, sir.
I think if you can recall that thing. So
Yes.
what does mean? Like if the angle is smaller, the arc length is smaller, but if you go farther and farther, it will be much more sparser. Like in terms of the perpendicular distance, I'm not talking about the direct distance. Like if you go farther and farther, and if you want that explanation in terms of maths and equations, you can contact me. I can give you I have that solution. I need to find out that, or otherwise I can solve it once again. It's fine. It's very easy solution. Like let's say if you can calculate the in terms of radius and the phi theta, or over here is phi, yes. And from that S, you can calculate the perpendicular distance between this and this, like this one. And you can easily observe the perpendicular distance. Variation of perpendicular distance is much more sparse than this region. Over here, it's much more denser, because over here for this region sources, you have contribution to the actual time, what can I say, the station pair distance XA minus XB. If you go further, the relative distance between XA and XB getting less, which means the influence is getting smaller. So that's why the influence are getting very smaller, and it is getting like this. For this region, it is getting like when you are stacking this up, it is getting blowed up. That's why it's kind of high peak over here.
So is it a similar concept that we read in the directivity of the sources? Like when the source is at the 180 degrees, then the time is maximum, and when it is at 90 degrees, it will be minimum. The same thing, right? Directivity of the source effect.
Oh yeah. Directivity of source is directivity of that's a different. Oh yeah, actually you were partially correct. It's fine. Yeah, but like that's kind of that assumption. Like we are assuming that the source is uniform. That's why. Like in your case, the thing you are talking about, it has a prevalent azimuth of the source, right? The direction is but the assumption is not valid over here. We are assuming that it's kind of uniform, which means that the major influence will come from this and this end, like from 0 degree side and the 180 degree side, and there's some other partial region. So let me.
You mean to say at sir?
Yeah.
Sir, you mean to say at those phi, you can say the sources are more coherent. Can we say like that?
Yeah, like actually, all like the thing is that if it is not coherent now, like what will happen that you will get more coherent sources in this region, it's fine, but because of that incoherent signature in this part, it may happen that it can contaminate this part, like this in the middle part. It may happen that you will get some small extra spikes over here.
Yes, sir.
Because you have to think about that incoherent source as different structure in terms of arrival time, because the phase getting distorted, right? Phase getting distorted means when you are stacking the phases, like over here you are just like, you can think that you are stacking the phases, right? You are stacking the waveforms means the phases are added up. Like if the phases are constant with time, the phase difference is not changing with time, which means that there will be no blow up of phases. Let's say according to your cases, like let's say if I think the phase is not coherent outside this hyperbola, let's say. So let's say it may happen that over here you'll get a different kind of wave, and over here in this part, or maybe in this part you'll get a different kind of wave, or maybe over here you'll get different kind of wave, and over here different kind of wave, which can give another small recorrelate like this, similar like this over here, because the phase got distorted, right? Because of the incoherency in the sources, which means like your thing is correct, because in the real world problems we have incoherent sources too, and the coherent sources is much more lesser than incoherent sources. So in that case it happens, but ideologically by assumptions it is coherent. If it is not coherent, you cannot get this kind of thing. You will get some other waveforms in middle, because there will be other phases too which is distorted, like which is not consistent with this one and this one, because over here you can see the phases are consistent. It's kind of positive wiggle, negative wiggle, positive wiggle, negative wiggle, right? But it may be distorted, like if it is not coherent. So yeah, so next up, it's a 2D thing. So for the 3D thing, it's kind of, I think it's easier. You don't need to think about right now. So if you want to do the reflected wave interferometry, which means the body wave interferometry, it also can be done, but it's really tough to observe the body wave, because it's like for very specific cases, you can observe the body wave from the ambient noise sources. So what happens over here in this theory, we think that we have two receivers placed over here, and there is a source at the deeper part of the subsurface, and we get waves from that source at XA from the left one, and we also get the reflected one, which is bouncing back from XA location, and from this point, from this, we can also call this as a CDP or CMP, common depth point. So and also from that reflection, it is coming back to XB. So if we cross correlate these two, the XA and XP, will get the reflection response uh, of the subsurface media. But there's a catch over there. You can easily ask me that what is the difference between then surface wave, the direct wave, and this one, because all are cross correlations, right? But the thing is that there are a lot of differences that, so when you were checking the cross correlations in frequency spectrum with various arrival times, you can see the dispersive nature for the surface wave, whereas for the direct wave and for the reflected wave, the dispersion is 0, which means for all frequencies, the travel time will be same. The velocity will be same. The velocity will not change, means which means there is no change in velocity. There is no dispersion. So for this one, you will not observe any dispersion, as well as over here for this one, the arrival time will be much more faster than surface wave, though it is much more slower than the direct wave, but it is faster than the surface wave. First, direct wave and surface wave, I think you all guys know that those two things are different to each other. So before going to the physics, if you want me to go into the theory part, like how it's getting modeled, I can give you a brief overview. I think I should do that right now. Then I can, if you want, then I can cover this part. Let me come to that one. Just hold on. Hello, can you see my screen?
Yes.
Yes.
So over here, I think you got the brief because, yeah, because I think I can uh, pass you the basic structure or the flowchart of doing this tomography. So basically, I don't want to go through this whole stuff. If you want, you can go and read this, but I want to make a basic
This is Benson paper.
it's a Benson paper, yeah. So in the Benson paper, what they do like, I think a good survey followed this flowchart as well. In that part, what they do, as they are doing the surface wave tomography, not the direct wave arrival, not the body wave, only surface wave, which means they should observe dispersion, and that's their main objective, to create a subsurface model. So the dispersion means for they should observe the different arrival time of the wave for different frequency bands, which means here is an example I need to show you. It's a cross correlation station between Albuquerque and Harvard, Massachusetts. You can see the cross correlation, the actual raw cross correlation is over here at the top end. You can see it's very nice and smooth. But if you make a filtered response of the actual cross correlation function, you can get this kind of window panels for first, second, third, fourth, fifth. Okay, so further you can see the arrival time for this window and the arrival time of this window is different, which means the wave is dispersive and the wave you are considering, that is surface wave, not the body wave, not the direct wave. Also direct wave is also a body wave. So second thing is that the pre-processing part, it's very quite tricky and it's very important for processing the ambient noise. As you know, the ambient noise data is kind of continuous time series data. So you can do two things. First of all, you can have cross correlation of the two whole seismograms. Like let's say you have seismogram of 1 day data. Let's say 1 day, you have data for 1 day. You can do one thing, you can just cross correlate the whole 1 day data in a single time, in a single shot. Otherwise, you can do what you can do, like you can just truncate the whole waveform in hourly basis, like in 24 hours, means 24 windows, and then you cross correlate in for 24 sections, and then you can stack it up. So what's the advantage and what's the disadvantage of this? First of all, if you have a very time consuming source, let's say, which is going forever, let's say some ocean wave is coming from one end to the other end for the whole day, which means, let's say, if you truncate the whole 1 day seismic waveform, and then if you stack it up, I mean, if you cross correlate and then stack it up, what will happen? The source signature of the ocean wave will not be removed because it's consistent throughout the day. Now, let's say someone is driving his or her own car nearby to the receiver end just once in a day to check the status of these receivers. What may can happen, like I'm just giving you an example. In that case, what will happen that if you stack in an hourly basis, it may happen that as you are stacking in hourly basis, which means, let's say he came with his car at 10 a.m. in the morning, and for the 10 a.m. cross correlation section, 10 a.m. to 11 a.m., you will have that response of that Jeep or maybe some car. But it may happen like it will happen that after he leaves the site, there is no response from the Jeep or any car, which means if you stack all these hour sections, the effect or the influence, please make a note over here. The ambient noise is all about the influence of the source, the priority of the sources, which means the priority of the source get diminished. The source signature will be there, I know, and we all agree about that. The source signature from the Jeep will be there in the stack section, but it will not give any significant amount in terms of amplitude because it's just a transient source for an particular hour, because after that there is no source from that end. So that's another thing. And beside that, what we need to do, we need to, as we know that we have different kind of geophones, or not geophones, I should take about receivers. We have broadband receivers, we have accelerometers, we have low frequency receivers, high frequency receivers, as well as the geophones, which is very common in the exploration seismic studies. So both all these instruments has different instrument responses. So what do you mean by instrument responses? The instrument response means the poles and zeros of the particular instrument. Poles and zeros signifies the phase information, the amplitude information, how it changes with the vibration of the subsurface. Like if we have different poles for different instruments, in that case, if we don't eliminate those poles and zeros, and if you don't normalize that, what will happen that it may add up some other phases too, because poles and zeros are very important. I think you all know about what do you mean by poles and zeros, and I think you did that in the digital seismic processing or in your undergrad or master's level courses. So over here, it's a kind of basic structure or the flowchart. It's kind of you, if you have raw data, what you do, you just remove the instrument response. I think I just told you that. Secondly, as we need to remove the mean and the trend, why do we do that? Hello, hello.
Yes, sir. Yes, sir.
Yeah. So
It's
actually,
all
I
right.
can't see you guys, so that's why. Yeah. Uh, so what do we do that? The removal of mean and trend. The removal of mean helps to remove the DC component of the signal, as we cannot do anything with the DC component. Or DC component, the continuous component. And the second thing, the trend is very important, because as we know that it often happens that we have a very, very low frequency part of the seismogram, which is giving us the very low frequency trend. It may be an exponential, it may be a sinusoidal, it's very low frequency, like it's an ultra frequency, but it may happen that it is coming because of some issue with the instrument, or maybe some data recording issue. So what we do, like we remove the trend as well, and which means we are just eliminating the modulation. Here the trend removal, it doesn't mean that we are just removing the very low frequency signal. It basically means that we are demodulating the signal. I think you all know the demodulation of the signal, definition of the demodulation. If you don't know, please you can ask me, I can just show you an example of that. So after that, what we do, we like over here you can see it is telling that they cut to length of 1 day, because but it depends on your objective of the problem. Like let's say someone is willing to do the very shallow seismic study, like the civil engineers do the very shallow seismic studies, like for the soil mechanics studies and all. In that case, you often use hourly stacks or minute stacks, because your main concern is to very shallow subsurface, as well as minor sources like the car, jeeps and all, because you are not considering very regional kind of sources or very large sources like the hums or natural hums, or maybe ocean waves, or maybe wind, hurricanes and all. Maybe you were just considering the human noises and other kind of stuff, or infrastructural noises. In that case,
but in the hourly data also, the effect of those natural sources will be there, right?
Yeah, but for hourly source it will be there, but it depends, like if the source is consistent, that will be there. Let's say if you don't have any, like let's say if someone wants to characterize the source which is coming from a building or maybe some bridge, in that case the hourly stack may hamper that one. They need maybe the minute stacks and all, because if you shorten that stuff, shorten the time, which happens that the like it will blow off the minor effect of the sources. Like let's say some sources which is getting drained because of very large oceanic waves, That may not happen if we do a short stacks, like basically for very transient sources. So I think I can come to that part later, because it's very much variable in terms of the study, the purpose of the study, and the motivation of the study, also the location.
So 1-day data is needed for doing a deep earth study, right?
Yeah, like 1-day data means, like 1-day data cannot give very unique solution. First of all, for, let's say, it depends on the deep structure, like how deep you are going. Let's say if you want to go towards mantle, or you need at least a couple of months of data, because 1 day cannot give you very unique model, because there I think, let me change this. Can you check? Can you see this paper, the earlier one?
Yes.
So over here, this, you can see this response over here, right? Figure 6E over here, because if you don't have enough data, just if you just cross correlate things, in that case, you will have some zigzag noises over here, or maybe here. So that may not give you the very unique model, according to my personal experience.
So
That,
how much minimum amount of data is needed for doing reliable modeling?
at least 1 year,
At least 1 year.
because at least 1 year, 6 months of data is fine, but it often happens that for 6 months of data, you don't have enough coverage of the data for the entire 6 months. Like when, like in some cases, what will happen that some part of the region has the data from January to June, and some part had data from July to December, something like that. So in that case, uh, at least you need data for an year or couple of years, maybe 2 years. But if you have consistent data for 6 months for the whole region, I think that's fine. You can go with it. It's fine. Like 6 months of data for the whole region from January to December is fine.
For all the station.
Like, yeah, like you can go ahead and you can just do the tomography. It's fine.
Hello,
So
sir.
is there a limitation on the inter-station spacing also?
Yeah, it's a very important thing. Like, yeah, let's say we know that Fermat's principle and all. Basically, it should be lambda by 2, but the focus wavelength, like we should have a prior model of the velocity of the subsurface. From that prior velocity model, we should have our target wavelength. Using that target wavelength, we can use those station pairs which has the interstation different distance, at least, like for my experience, even lambda is not enough. I consider as 3 lambda. 3 wavelengths should be there in between two stations.
Minimum or maximum? Minimum.
Sorry?
3 lambda is for maximum distance. I like, let's
maximum. Like it's a nominal. Like it may be more than that, but minimum should be at least 2 lambda, 3 lambda. Because for my case, I like to use 3 lambda, because if I go towards 2 lambda, it may happen that I'll face aliasing. So then I need to use the anti-aliasing filter. So I want to avoid that anti-aliasing filter, because it often happens that the filter can remove some important features from the target Green's function. That's why my whole intention is to avoid that strategy using anti-aliasing filter. So that's why I try to make it like that, like 3 lambda at least.
okay.
So yeah.
So like, let me just point that out here. Like for our stations, I think our inter-station spacing will be minimum at least like 100 kilometers. So is that fine?
Yeah, so that's the criteria. Like, let's say if you're considering the interstation distance as 100 kilometers, if we consider it's as a 3 lambda, I'm thinking about that. Let's say I'm thinking it's a 30 kilometers is a lambda. Let's say if lambda is 30 kilometer, which means that you are considering the velocity of 30 kilometer per second if the frequency is 1 hertz,
Yes.
which means you are very good to go. First of all, you don't have any problem because 30 kilometers per second it cannot be, right? Which means, let's say for the deeper structure, for the mantle, your frequency is how much? Your frequency is, let's say, period is around 1 by 40. Let's say for the mantle, your frequency is 1 by 40 second. 1 by 40 is your frequency.
Yes.
And let's say your lambda is 30 kilometer. Then what will be your velocity? Your velocity will be 3/4, 0.75.
0.75, yes.
0.75 kilometer per second. So you cannot achieve that. You cannot achieve the mantle modeling using that one. You cannot achieve the mantle modeling using that much of interstation distance. Let's say if you consider, like, you can achieve, but there is a lot of non-uniqueness. Like, I am over here, my concern is that 3 lambda is not a logic, or it's not came from any equation. Basically, at least if you have lambda separation, it's fine. 1 wavelength is fine. But like, according to my experience, or also the other papers, if you go through the other papers too, like in that paper, they have suggested that, like, yeah, 3 lambda is very good to apply on it, because like, then you are in the safer side, first of all, like the safer side from aliasing phenomenon. Yeah, so like, if you want to, like, if you are considering that lambda as your if you're thinking lambda is 50 kilometers and your interstation distance is 100 kilometers, then I think it's fine, you can go ahead. But 2 lambda is often think I'm little bit of concern, because as we don't know the prior model of that subsurface, right? Because it often happens that the prior information of the velocity model which we are getting from any kind of geological study, they have some kind of surface based modeling, the rock based modeling, right? In that case, the surface based rock formation modeling cannot constrain the velocity, actual velocity of the mantle. So that's why we use that kind of thing, that kind of assumptions, like 3 lambda. Yeah,
Okay.
so basically, yeah.
Okay,
Second,
thank you.
yeah. So basically,
I have one question.
yeah.
So suppose we have 12 or 10 seismic stations, and if suppose we are cross correlating the data of one day. So suppose we have a situation like, if we don't have the record of 5 stations data for the particular day. So in that particular situation, what we should do?
Can you repeat your question? Like, I'm a little bit confused. Like, you are telling that you have you have 10 stations, right? And you have 1 day of data, right?
And yes, sir. If suppose we are cross correlated 1 day of data.
Then?
And then if suppose in 5 stations there is missing that particular day of data. So on that particular situation, what we have to do?
So let's say it depends on the location of the receivers. Let's say you are missing the data of those receivers which are in the middle, of that region.
Okay.
Let's say in that case, what will happen? You will lose the uniqueness of the model in this region because you are missing some stations. But if this happens, that the stations, the data from the stations are missing from the outside of the region, right? In that case, what will happen? You will basically you will not have any model basically, like in the outer part of the region, and you can, for that case you cannot extrapolate the model, because uh, because if the region if the stations lies in the outer part of the region, it often happens that uh, the small cross correlations which are doing the, like for the small interstation distances, you cannot have that model, which means the small velocity contrast, what you can observe if you had data, you will not have that. So basically, if your data is missing, it's not a big deal. The basic drawback is that your model will be non-unique, and also I'm not being subjective about that. I'm like, if you want to calculate the resolution matrix from the observed model, you can easily see that the uncertainty or the model for those regions where the data is missing, it's much more higher, a lot higher. Like, so that's a thing. Otherwise, yeah, if you want, you can interpolate the result. Like, it's, if you don't have, you can't like make up that, but it's fine. So yeah,
Yes,
so
sir, you are
basically,
correct. Like if suppose the stations lies in middle of the uh, study area, then it's okay. If suppose it's going outside of the study area, then it should be very difficult to interpolate or extrapolate, or might be our result will non-unique. Na?
yeah, but if you are, yeah, so the thing is that, like, if those stations lies in the outer part of the region, what will happen? You will lose some uniqueness of the model in the middle as well. Why is it so? Let's say you have a region, and in the middle part you cross correlated that part. You have, sorry, you have calculated the velocity model from the small station pairs which are situated in the middle, in the central part of the region. Now let's say you don't have the stations at the very end, which means the uniqueness
Mhm.
which you may have, that using the cross correlation between those two outlier stations, that let me, I think, let me draw something. I think that will be much more easier for you. I think, let me, I think there is a tool for, can I say, can you see my
Yes, sir. Yes,
screen?
sir.
Yeah. So let's say you have this region. So you have station at over here and here. Now
Yes.
this station, and let's say you have another station over here and the station over here. So this pair, this pair, this pair, this pair will all help you to constrain the region in terms of model, velocity model, right? Let's say if you have more stations over here, I'm considering this as outlier stations
Yes.
over here too. Which means you can also use these station pairs, right?
Yes, sir.
Which means when you are inverting the uh, group velocity or the phase velocity of the surface wave, you are doing that for this pair as well as this pair, right? Let me color it. So this, let's say if you're going along x-axis, so you can do this line,
Yes, sir.
And you can do this for this line, right?
Yes, sir.
So you have two ways to quantify this region along x-axis,
Mhm.
which means you have more certainty, right? Like you need to fit two waveforms. One is this one and one is this one. So that's why, like, it will bring you more uniqueness. If you remove this thing, let's say, if you, what is this one? If you remove this one, then what will happen? You are only dependent on these two, this station pair.
Yes, sir.
So it why I am telling you that, because in the paper I'll show it to you, like the paper I'm considering right now, the Benson and the Barman. In that paper, like in the real world situation, getting dispersion curve, it's really tough. Like it's not like just you cross correlate and in the fraction of time you'll get the dispersion. It's not simple as that. Like getting dispersion is quite difficult. Like it's a lot difficult. So
Yes.
yeah, so that's, so after that, what do they do? Like normally, like we do estimate the groove velocity or phase velocity. It depends on what you want to do. So groove velocity, you just do, like, I think you know about the basics of groove velocity and the phase velocity of any kind of wave, right? Like the groove velocity is the velocity of the whole group of the wave. I think I have some animation to it.
The entire energy packet.
Sorry?
The velocity of the entire energy packet of the
Yeah. So the thing is that why we consider the phase velocity in the surface wave, because surface wave has a unique property to identify the phases and that will provide the high resolution tomography. But there is a very big drawback of phase velocity modeling using the conventional method, is that phase velocity has a very big problem regarding cycle skipping. Like when you are matching the phases of the waveforms to calculate the phase velocity, it often happens that if it less than lambda by 2, you may miss the cycle. So it often happens that we land to any very unreliable velocity model. So in that case, uh, we cannot get our relevant solution. So most of the time people go through the group velocity inversion rather than using phase velocity. But phase velocity is also very good to use, like if you can validate your cross correlation functions and all, like if it's very clean and if you can identify all the phases very clearly, then it's like you're good to go to use the phase velocity inversion. And the fourth one is that it's not about, I'm not talking about this phase fourth thing in this over here. I'm talking about the fourth part, is that like if you have the group velocity or the phase velocity measurements, then from that you can get the group velocity or the phase velocity maps for the whole region, as well as if you want, you can invert those maps to obtain a very relevant shear velocity model, the SOF velocity model. But though this modeling part of the shear velocity, it's very non-unique. Like it often takes a quite dramatic step to land to a very relevant solution, because the equation they use, the Guterbe use, it's kind of basically 1D phase velocity modeling or group velocity modeling from the shear velocity, and it takes a lot of assumptions regarding the VP-VS ratio and the VP density ratio. So So yeah, so that's another thing. So now let's continue to the other part. I think this part. So over here, one thing I need to tell you that uh, our desired gain of the seismometer or broadband seismometer or geophone, anything you can tell, the gain should be set to a maximum value. At least it should be more than 12, so that if there is a response, some kind of source, it should blow up much more in a bigger amplitude, like bigger the amplitude value of those waveforms for those particular responses should be higher. That's why we should set the gain of our receivers at maximum. And if we set that, after that, what we can do, we should do the normalization of the seismograms, the continuous time series. So we can normalize the seismogram in two different ways.
So
Like,
normalization we are doing to remove the earthquakes.
yeah, 1 bit. Yeah.
Okay.
So why
Sir,
we're
what
doing
is the
it?
concept of 1-bit normalization?
So that is
Like, yeah, 1 bit normalization is that, let's say, I think you cannot like, it's really tough to understand from this figure. The basic fact is that 1 bit means if there is a positive value, it will go to the maximum 1 bit, and if it's a negative value, it will go to a maximum negative bit, negative 1 bit. And this way, what will happen, that you can see in the figure B, like in this figure 3B, you can see it's kind of like just, there's no particular shape of waveform, it's just zigzag, plus minus, plus minus, plus minus, because it's kind of represented in a bit 1 bit format. So what we do then, we just apply some normalizing equation, like it's kind of scaled equation. From that scaled equation, what we do, like those numbers, amplitudes which are greater than the possible earthquake amplitudes, let's say we have earthquake amplitude like 5 or something like that, some numeric values, we just eliminate those parts. So as simple as that. So after this, what we do, that we cross-correlate the continuous time series. Over here you can see an example over there. So after that, let's come to the fun part. So yeah, over here I need to make a note over here: spectral whitening or normalization. Spectral whitening is often used for to eliminate the amplitude variation of the seismic responses from the cross correlation, but in regular conventional ambient noise tomography, we don't use that spectral whitening because it may affect the responses, because it may blow up some extra phases. So we often, yeah, like it's on your own risk. Like if you want to use that, it's fine. But in conventionally, we don't use that because it may blow up some of the phases, like which are not there or something like that. So blowing up phases reflects to incorrect calculation of the travel times that propagates to the error in the velocity model. As simple as that.
basically this step we need to skip.
Yeah, you can escape. Like it's kind of for your own risk. Like you need to test for a couple of times for different station pairs.
Okay.
So yeah, so let me go to the dispersion measurement. So the dispersion measurement, I think I just discussed with you that it's kind of just conventional filtering of for different frequency band or period band, and then obtain the travel times. But over here, it's not that so simple procedure. It's really complex. First of all, what we do, we in the first part, we filter the actual cross correlation function for different frequency bands which is also called as nominal periods. From that, what we do, we recreate those signal for different frequency bands using a analytic function, which means we can represent the actual raw cross correlation or like raw cross correlation in frequency domain in terms of an analytic function. So the analytic function is represented by this equation 3. So what is the importance of analytic function? I think you already know what is the importance of that. First of all, it happens that it helps to smooth the plot. It's kind of very basic, it's kind of very layman kind of term, but in physics we should say like that. The analytic function, it helps to translate this nominal windowed Green's function into a instantaneous frequency Green's function. Basically, we need the dispersion curve or the travel time for each frequency bins, right? 1 Hz, 2 Hz, 1.5 Hz, 2 Hz, 2.5 Hz, something like that. But in nominal frequency, what we have, nominal frequency means this is the nominal frequency. Let me give you the idea of that. The nominal frequency means this is your nominal frequency, 7 to 25, 20 to 50. These are the nominal frequencies. But the instantaneous frequency, you have waveforms at particular instances, in particular periods, like specific discrete periods. So yeah, so after doing this, so what we do, we just like this is like a transfer function. It is often called transfer function, or you can, like I call it as transfer function, but you can think as that Gaussian filter, where it's kind of this alpha is very important. This alpha parameter smooths the dispersion curve plot. Otherwise, it will be very spiky and all. So yeah, alpha, it depends on the interstation distances. But for my case, I often use 10. Sometimes it's 50. So yeah. So another thing is that, so instantaneous frequency, you can identify or define the instantaneous frequency as d phi dt. So wherever t is the tau of omega, which is the time lag, the arrival time of particular central frequency, omega naught is the central frequency. You can ask me if you want more about that. Like there's a full proof and like it's kind of proper derivation of this thing. Like you can, if you want, you can just read that thing. It's simple. It's not a big deal. So what we do that, like what's the reason behind that? So the, like if you don't do this instantaneous frequency analysis, what will happen? Like using that nominal frequency, you cannot build a total dispersion curve because you don't know the intermittent frequency time values, like arrival time at particular frequencies. Let's say you have these plots, you have 70-25. If I ask you what is the arrival time at for period equal to 20 seconds, you cannot tell, right? So if you don't know what is the arrival time for 20-second period specifically, then you cannot get a very smooth dispersion curve. That's why you need a instantaneous period function to make a dispersion curve very smooth. So for that purpose, you need this transfer function. So this, after this Gaussian filtering approach, you just calculate the derivative, first order derivative for each central frequencies, and that can help you out to get the instantaneous frequency spectrum. But over here you can see there's a term called spectral leakage. Spectral leakage is the same thing I just discussed it right now. Like if your central frequencies cannot accurately represent the arrival time or the velocity, which means you have very zigzag kind of dispersion curve, which is not very smooth. So now let's go to the second part, group velocity measurements. So I don't want to read this thing. I think you can, it's very simple. It's not a big deal. So what is this thing? Let's say you have this blue is your actual cross correlation. And from this blue, you are getting the dispersion curve measurements like this. This is this B, figure 13B. You can see some blobs are there, right? Some yellow red structure is over here, and it's not very smooth over here. Some things are over here. But if you look into it, you may think like that, oh, it may be the first or sorry, it's maybe the first harmonic or the second harmonic of the surface wave. It may not be the fundamental mode, or maybe you think like that, oh, maybe it's a body wave. It's not dispersive, right? The first small one. And you will be very happy that, oh, I see the body wave, but it's not. Or it may happen that it's a body wave. So what happened that it may happen that it's body wave. So basically, like in your study over here, your primary concern is the surface wave, which means you want to eliminate this kind of very like noisy things, those arbitrary signals or arbitrary noises in your plots. So what you do, first you try to collapse those signals, those noises, which is the part of the non-dispersive sources. Non-dispersive sources means not sources, like non-dispersive waves. So non-dispersive waves means it may be the body wave, it may be some earthquakes, or maybe something else, something like that. So in that case, what they do, or what the flowchart do, the strategy is something like that. You recreate the synthetic cross correlation by using a phase matching filter. So the phase matching filter, I think it's not over here. The phase matching filter gives you, like phase matching, the primary objective of the phase matching filter is that it check all phases, all other phases, all like the phases of these waves with this one. And if it's not matching with that, it will collapse. It will give you zero output. So that's why it's just a zero. So let me tell you, the plot you are seeing over here, like it's a, like you are not observing the actual velocity actually. What you are observing, like if I zoom it out, like you can't see right now, it's actually stack or the representation of all the cross correlation in the time domain. Means the like the whole section, like over here, for all periods, means we can say it's as a frequency, like if you are comfortable with it, like for all periods / for all frequencies, you have a cross correlation function, right? So you can transform that cross correlation function in terms of arrival time, travel time of the wave. It may be the group velocity, it may be the phase velocity, but for this case, we are considering the group velocity. So the group velocity is the travel time or the arrival time of this maximum amplitude, as simple as that. Or maybe you consider this one. So if you plot this one, you can see for regular cases, as these waves are non-dispersive. Why it is non-dispersive? You can see it's just a blob, which means over here for all periods, the velocity is same. For this one, for this much of period, the velocity is not so, it's not validating the physics like over here in this part, which means it is the contamination. So what do they do? The phase matching filter. With the phase matching filter, the main working principle is that it matches the phase of these waves, which is creating these noises, with this one. If it is not matching with this one, it just make it zero. So that's why it is something like that. So which means the non-dispersive things got omitted and you will get a clean dispersion curve. So it is often called as a raw dispersion curve, and this is often called as clean dispersion curve. As simple as that. I think this is fine. And I think there's another paper by Barman. I think, yeah. It's a, this paper is also important for the 2D maps of the group velocity. So in that case, what we do, as you know from the whiteboard, okay, whiteboard, you have station pairs, sorry. You have station over here, over here, over here, over here. So you have lines like this, right? Ray paths like this, great circle paths. But let's say if you want to have the group velocity map at this location, what it should be. You can do two things. First of all, you can just directly interpolate from these, all these maps, all these dispersion curves for this one, this pair, this pair, this pair, this pair, something like that. But you need to make some weights, right? Which pair should have influence more for this location, right? So that's why we take care of Delaunay triangle. It's kind of a triangulation theorem where we can interpolate any point using vertices of the triangles. So I can just go back to that paper, I think, yeah. So let me give you an overview. So it's, you can see an example of Delaunay triangulation over here. Like you can make different Delaunay triangles out of grids, out of regular grids. So what you do, the main purpose is that, let's say if you want to calculate the dispersion curve at period P, using these these four dispersion curves, you try to fix weights W1 into this, W2 into this, W3 into this, W4 into this. So W1 into this plus W2 into this plus W3 into this one at P frequency, the P period, and W4 into this will give you the dispersion at P period at this point. So yeah, so now come to the fun part, little bit of calculus. It's not very tough. So what we have basically, let's say we have travel time and we have the distance ds, right? So we can write the travel time in terms of this, like it's kind of p is the path, the line integral, and c inverse is the 1 upon velocity. We can often write down as the slowness, because if we consider this as slowness, which means it's a linear equation, and we like linear equation because it's easier to solve. And let me know if you feel boring about this stuff, then I can just move forward a little bit. So what do they do? Like for the for problem, let's say to calculate the weights, let's say for this one, I think for this calculate the weights, we need to first figure it out. We need to figure it out for which points we need to calculate, right? For each periods, we need to figure out the grids and the time residuals. Like these weights should be calculated in such a way that the travel time residual, like travel time residual means the travel time between this and this and this and this should match with the synthetic travel time residual. I think I can give a more better view from these equations right now. So let's say you have a mean velocity model C naught. You don't like you considering C naught as some velocity model, initial velocity model. So what you need to do, you want to calculate the actual C velocity for a particular dispersion curve. So for the 2D reference map, you have C naught for all the radial points. So for the time residual, you will have these equations. And where m is this is a fractional change in velocity, right? So this velocity can be written in this format. This is because it's in spherical coordinate system. So I'm skipping this part because it's simple. So now these are you can just easily get it from any book or something like that. It's very not a very tough. So now what the inverse, what we want to measure, we want to measure the error between T observed. The T observed means the arrival time of that group of that cross correlation function from the synthetic ones. If we have the velocity C naught as initial velocity. So our residual is T observed minus T, and it's very important. This is the actual tomography part for the group velocity. So we have T observed. We are considering T naught, which comes from the C naught, is the reference velocity model, and it's our epsilon is the error, right? So now we can construct this parameter so that we can easily represent our equation in much more simpler format. So if we use CI instead of C naught, then we can easily use parameter M, because M can give you the fractional change. It's not actually fractional change. It's kind of pattern, like it is kind of, it gives you an approximate ratio between the CI and C naught, right? So over here, this is called the kernel matrix of the linear problem, the D equal to GM format. I think you already familiar about that. So this is the linear equation, right? Just hold on. I think they haven't mentioned. So it's if for the linear problem, we know that D equal to GM, where D is the data, M is the model parameter, G is the kernel matrix. So we simulate the G in such a way and model such a way that we can get a linear problem like this one, sorry. So over here, we have constructed G as this, and we have D as the delta T. Delta T is the time residual, and GM is the fractional change. I think I discussed this one. So and we just minimize the residual, as well as you also minimize the model parameter to make it very sparse. So there are two basic fundamental strategies to constrain the model by constraining this function. I'll discuss this later. This is called f of m, and this is h of m. So what do you mean by those functions? F of m is controls the smoothing of the model parameter. So f of m is kind of write down like this. So what it does, like how well you want to smooth the model, it's basically depends on the user specific thing, because you need to input this sigma. It is often called the correlation length. It's not cross correlation, it's just a smoothing width or the correlation length. It is user defined. You need to provide this thing while running the code. And also this alpha, like how well you want to smooth the whole velocity model. And this is very important part, this hm tells you if you don't have enough ray coverage in a particular part, that part shouldn't perturb more while inversion, which means that let's say you want to model the point, the velocity model over here, and you know there is no enough ray coverage in this location, which means if you are getting too much high low perturbation values over here, we shouldn't consider those values. So that makes much more smoother model where you don't have enough ray coverage. So like, and these functions are very self-explainable. It's not very tough. And this is lambda is also user defined, like how you want to do. And it also depends on the path density. I think I just discussed this one. It damps those perturbations. Yeah. So after that, the interpolation part, yeah, I think I just covered that one as well, the Delaunay triangulation. And now here again, the inversion matrix, I think this whole thing, where is this equation? So this whole equation can be represented in this kind of parts, constituents, like this one, where this is, and over here, C is the covariance matrix of the error. I think you already know what is the usage of covariance matrix while doing the inversion. If you don't use the covariance matrix, like we cannot constrain the error of the, like while inverting the model. Like covariance matrix of the error means the error which you're getting for a particular model parameter with the other model parameter. Let's say how dependent M1 is towards M2 in terms of error. So that constraint that helps, like this kind of covariance matrix of error helps us to constrain the whole inversion, inversion algorithm. So yeah. So now these are the strategies to solve that. So if you want to know more about that, I can discuss this more, but if you want to go towards, yeah, so now it's a very important part. I think you just discussed about the resolution matrix. I think you guys asked me about like if some data are missing, what will happen like from the outlier stations. So in that case, you can see the resolution matrix. What is the resolution matrix? Basically, the resolution matrix is a like linear transformation between the actual model parameter with the estimated ones. So if the resolution matrix is a diagonal matrix of 1, which means like, or you can say that it's an identity matrix. If it's an identity matrix, it means you are getting a very unique solution. But we often get a very non-unique solution, which means there are many non-zero values for any non-diagonal elements. So to measure that, we often take care of this formula, and it came from the equation earlier, as we know that D equal to GM, and you can write down M estimated as this function. Like this is the M estimated, right? So which means that if you invert that, like I think it's being taught in the inverse theory class. I think you already did that, the geophysical inverse theory in your final year. Like it's over there, like how we measure the resolution matrix for underdetermined problem and the overdetermined problem. So it's very basic, like you just take the transpose of that and you just multiply and you'll get the resolution matrix in the form of this. So this is your resolution matrix. Or if you add Q, because over here Q is not there. If you add Q, the Q after adding the resolution matrix will be like this. So if this value is an identity matrix, which means you are getting a true solution, unique and true solution. But often it is not. But the resolution is often really terrible to acknowledge the actual uncertainty of the model parameter. Though that's why what we do, we recreate or reformat the resolution matrix in this kind of conical structures, where we this is the matrix basically.
So
We divide it into lat long, and we try to map a conical value where the diameter of the cone is the standard deviation of the resolution and the peak value is the actual velocity. So if it matches with the observed ones, like this one, like then we should get a very less value, and very less value means you have very good resolution, means the cone matches with each other. So low amplitude value means higher resolution over here. But this amplitude is not same as the amplitude of the resolution. That's different. This is the cone matching thing. So now I think I have covered a lot of it, other than the Bob Harmon's code for inverting the shear velocity model. So now if you want to get to know more about the code of the Gotorbe, so I'll suggest you to do one thing, that one of you should show me the code means the path and the terminal, and I can help you out, because if I share my screen I can share it, but the problem is that like at my university, like all those Python environments are depreciated, the older ones, so I cannot run anything because on to Python 2.7 basically, and that whole Gotorbe code was written in Python 2.7. So it will be much more beneficial, like if you can show me you're using by sharing your screen, I can help you out like how to run it. Like it's not very difficult.
Yes, Debjeet, thank you so much. But the thing is that we haven't started to install that code yet. So, so what I am expecting, if possible, anyhow, just for the benefits of the students, can we arrange another session where the student will show his efforts, what he has undertaken for installation and the other thing, path and other thing in the Linux environment for the Gotorbe code?
Yeah, sure.
Maybe next week or maybe next to next week. So in between, whatever you have taught us today, it's so we need a very good revision of that. So we know the relevant papers like Wapinar paper, Benson paper, Barman paper, other papers that you have talked about. So we can go through those papers. Like I will ask my student to read those papers properly and then give a presentation in the lab. Okay. So that we can understand more about it, and then we will go on to the code and then install it and also try to run it. And then we will come back to you. We will come back to you.
Sure. But make sure. So just 1 minute. Like I need to clarify one thing. Like try to create and try to install Python 2.7 forcibly, and don't try to install any updated version of Python, because if something some updated version of Python packages is there. It may not, like, it will not work. Basically, it will not work on that. So it needs Python 2.7 basically.
Okay.
So it's very simple. Just when you are installing the Python, if you have already installed the Anaconda, so first download the Anaconda and install it. It's very easy. Like if you are on Linux system, it's very easy. Just like go to the website of Anaconda. Like
I think Dheeraj has
download.
already installed it. Anaconda he has installed.
Yeah. So just try to create an environment, Python environment or Conda environment using Python 2.7,
Okay.
and specifically Python 2.7, not the 3 ones. It should
Okay.
be Python 2.7.
Okay.
And after that, like, yeah, it's very easy. Like just clone the whole directory from the GitHub, and yeah, like, and you need to like install some minor packages, like small packages. It's not a big deal. And the best beneficial part of Gutenberg code, it's very easy to run, and you don't need to um, uh, tackle any kind of fine parameters about that. And secondly, mm, it will give you its plots as well. Like you don't need to get tension about like how the plots will be, and it will generate a book of all the dispersion curve plots and the group velocity map plots with its file names. It's very simple. And uh, try to don't try to mess with the Python environment. Also, there is a directory inside it. It's called PySysmo. So there are a lot of functions inside it, and don't try to mess with that, because if you change something, it may hamper to uh, store the data, like the pickle files. Like it stores the dispersion curves and all, right? So that's my point. Like, yeah, like try to be focused, like how it get to you, like the Python 2.7 and all. Like it will work very good, and I'll help you out to like constrain the models and all. Like it's very easy, not a big deal. Yeah.
Is there
So
any
and if you
backup?
haven't, yeah, sorry.
Sir, actually, I have seen that. So we need to provide the PySysmo path to the bash RC file. Is there any bash RC file in, sorry, bash RC file or some bash file in PySysmo also we need to change?
I think I am hearing the echo.
No, actually, what he's asking, like he's working on the bash RC file, the environment file. Okay.
Yeah.
So where he's trying to put up a path for the PySysmo thing. So he's talking about, is there any bash RC file that is available with you that he can just use it to put up all the paths? So paths, I think that is not possible, is it?
Like it's not possible, or basically if you want to add bash RC, uh, it may not help in you in the future. Because the thing is that, like, let's say if uh, like when you are working with other projects, like maybe for other Python versions, when you are loading the bash RC, it may try to access those PySysmo, and it may give you some errors. Because like according to my strategy is that you don't need to be add into a bash RC, because it's not needed, first of all. And secondly, when you if you are if you're all your code inside that directory itself, like then it is just accessing the PySysmo inside that directory, right? So which means you don't need to override the path in your bash RC. It's not needed. Like it's redundant. If you want to do, it's fine, but it's not needed basically. Like that's my point. It's not needed.
So, Debjeet, thank you so much. I think
Yeah.
we also need to do our homework first.
Yeah.
So, like, so we will try our hands. So, and we'll put in some efforts to understand that G Gutenberg code. I think B Gutenberg code. so that something we should try from our end, and if we find any problem, then we will certainly come back to you.
Yeah, sure.
And we will try to organize one more session, one more shorter version of this session, because I understand that you are very busy with your PhD and you are trying to pile up all the things together to graduate on time. So it was a very wonderful presentation.
Yeah, nice. Yeah, nice
that-
for me too. Yeah, it's an
Yeah.
awesome thing that we discussed a lot of questions. Yeah, and make sure like if you have any questions regarding the theory and all and the physics, you can
Yes,
ask me if you want. Yeah.
Yeah. So certainly we will come back to you. We need
Yeah,
your
sure.
continuous support to
Yeah.
surface wave modeling. Okay, so in between you were talking about Barman code. Are we supposed to do anything with the Barman code?
Bob-Herman code is kind of one in unique. Like we use Bob-Herman code to make the shear velocity model. Like it's also in the Gutenberg code. So it's a Bob-Herman code actually to recreate the phase velocity and the group velocity dispersion curves for from a shear velocity model.
Okay, so it's a forward modeling.
It's a forward model, and like direct inversion of that forward model cannot give you the actual result. So we need to use some global optimization problem. So in that Gutenberg code, they have used the Markov chain Monte Carlo, that AMCMC approach to address that problem. Though that is also sensitive to, it's very sensitive. Like if you just give any random values, it will not provide you any relevant solutions at all, and it may crash as well. Like it's very much dependent on the prior models as well as the VP/VS density ratio, and also the number of layers too. So it may not be like, you should be very like gentle while playing with that. Yeah, it's fine, like it's nice, but though it's a global optimization technique, but still it has a lot of drawbacks. But you need to play with along with your region and all. Like they do that.
So that is all, I think. Debjeet, thank you so much.
Yeah.
And we learned a lot today.
Yeah. Thank you so
Thank
much.
you.
Yeah, thank you for introducing me to your students. Yeah, thank you so much. Yeah, have a good day. Yeah.
Okay.
Yeah. Bye.
Okay, bye.
Bye.